From a modern perspective, the relevance of family ties in social phenomena may seem somehow marginal. But, on a second thought, we realize that kinship relations should be important in many respects and in many situations. Let us just make the following points. First, for most of us, family defines the primordial social context, especially regarding our cultural background. It is from that context and with that background that we jump into increasingly more complex social environments. Second, structural anthropology identifies localized kinship patterns, which we would now call the motifs of kinship networks, as the building blocks of cooperative social behavior, such as social cohesion, alliance, and reciprocity. Third, many present and past social processes are clearly driven by family relations. An example that should be well known to all of us is that of pre-democratic Europe. Until the beginning of last century, European governments were essentially a family business, run by a handful of closely intermingled families that ruled over millions of people over hundreds of years, the self-appointed noble families. This is a map of Europe in 1914, at the beginning of the Great War. The dots show the seats of 24 monarchs of that time. And these connections show their kinship relations. The darker the line, the closer the relation. For instance, the kings of Norway and Denmark were brothers to each other. Lighter lines join first, second, and third cousins. George V, the British king, is said to have thought that a global conflict over Europe could not last for more than a few days, because they were essentially a big family. Sadly, he was wrong. But he was never known for his particularly brilliant mind. In any case, one of his first cousins was Nicholas II, the last Tsar of Russia. At a certain point, they even became indistinguishable. George was also a first cousin of the last German emperor, Wilhelm II, as they were both grandchildren of Queen Victoria. Now, as soon as you move away from these famous characters, it becomes more and more difficult to find reliable data on kinship in real populations. In practice, it is still virtually impossible to get statistically significant data in the public domain to build a large kinship network, either for ancient or for modern families. This is why we'll study kinship networks on a model population, instead of attempting to work with real data. As you will see, the model is based on the European kinship system. We'll keep it as simple as possible, with the only condition to include both blood and in-law relations, always within a given generation. So, let us introduce the model. We consider a population formed by n men and n women. To define their sibling relations, we first assign exactly one man and one woman as children to a couple of the previous generation. In this way they become brother and sister. Of course, this is a very artificial children distribution. Our next step is then to reconnect each individual to a randomly chosen couple of the previous generation, with a fixed probability rho. For rho equal to 0, we keep the initial artificial distribution. For rho equal to 1, we obtain a children distribution that has been used in many studies on genetics and genealogy. This procedure completely defines the blood-sibling relations in our model population. Next, we establish n heterosexual monogamous marriages, with partners chosen at random, but avoiding brother-sister mating. This procedure determines the in-law relations. Once blood and in-law relations have been defined, we build the kinship network by first choosing one of the two genders. For instance, the men. Each man will be a node of the network. Then, we connect each man with his blood brothers and brothers-in-law. Just that. For the other gender, the network is statistically equivalent, so that it is not necessary to consider both at the same time. Summing up, our network represents intergenerational kinship within a single gender, and includes blood and in-law relations only to the first degree, that is, to the degree of siblings. The model has just two parameters, the number of men n, and the reconnection probability rho, that we have used to define blood-sibling relations. Let us first have a look at a few examples of these networks, for n equal to 100. For rho equal to 0, the network is always a set of cycles. This may seem a little strange at first, but this happens simply because for rho equal to 0 each man has no blood brothers and exactly two brothers-in-law. his wife's brother and his sister's husband. And the only possible network with exactly 2 connections per node is precisely a collection of cycles. For ρ equal to 100th, some of the cycles have broken into filaments, filaments have stuck to other cycles, and some small cycles remain intact. As ρ keeps growing, we find that cycles and filaments aggregate into a large component, but still there are some isolated small subnetworks around it. Finally, for ρ equal to 1, we see that the large component has become more complex, and the small isolated subnetworks are still present. Our task now is to make a quantitative characterization of these structures. We'll study the following properties. Number and size of connected components. Recall that connected components are precisely the mutually isolated subnetworks that we have seen in the examples. The degree distribution, which is the distribution of the number of connections per node. Clustering. Assortativity. And finally distances and diameters. We'll recall their definition later. The results correspond to several thousand numerical realizations of the networks for each value of n and ρ. At the same time, for each realization, we have built a randomized version of the network with the same number of nodes and the same number of connections per node, but directing the connections at random. These randomized networks are a reference case to compare the results on kinship networks. In this first plot, we have the numerical estimation for the distribution of the number of connected components for 3 values of ρ, and a population of 1,000 men. Full dots correspond to the kinship networks, and empty dots to the randomized versions. In the inset, we see the mean value and the standard deviation over the distributions, as functions of ρ. The number of connected components grows with ρ, showing that the networks become more fragmented. In kinship networks, it is always larger than for the randomized versions. This indicates that the level of cohesion of kinship networks is lower than expected by chance. Kinship networks appear to be more disaggregated than their random counterparts. This other plot shows the numerical estimation of the distribution of the size of connected components, for 1,000 men, and different values of ρ. The size is simply given by the number of nodes in each component. The distribution is rather flat for ρ equal to 0, but it becomes strongly bimodal when ρ grows, with a steep rise for small sizes, and a sharp peak at around 860 nodes. This peak is the evidence of the formation of a big component, as we have seen in the examples. Here, we have similar results for ρ equal to 1, and several values of the population size n. Note that the horizontal axes are now normalized by n. The distribution of the number of components becomes sharper and sharper as the population grows, around a well-defined fraction of the size. The inset shows a close-up of the distribution of the size of connected components, at the peak corresponding to the big cluster. We see that the peak becomes better defined as n grows. This suggests that the big cluster is a genuine giant component, which contains 86% of the nodes. In fully random networks of the same size and the same total number of connections, the so-called Erdős-Renyi networks, the giant component has about 94% of the nodes. This is again an indication that kinship networks are less cohesive than their random counterparts. Let us now have a look at the degree distribution, that is, the distribution of the number of connections per node, k. For ρ equal to 0, each node has exactly 2 connections. In that case, we have a delta-like distribution at k equal to 2. As ρ grows, the distribution becomes wider, and exactly coincides with a Poisson distribution for ρ equal to 1. These full lines show Poisson distributions for the same values of ρ. Poisson is the expected degree distribution of an Erdős-Renyi network. But we have seen a moment ago that the kinship networks for ρ equal to 1 are not Erdős-Renyi networks, since their giant components have different sizes. However, we find now that they happen to have the same degree distribution. Let us see what happens with clustering. Recall that clustering is a measure of the fraction of pairs of neighbors of a given node that are in turn mutual neighbors. Clustering can be defined in at least 2 ways. Global clustering is a count of the number of triangles all over the network. Mean clustering is an average over the nodes of the number of triangles containing each node. In the plot, you have numerical results for the 2 definitions as functions of ρ. The error bars show the dispersion over the set of numerical realizations. Clustering is very small for ρ close to 0, when the network is a collection of cycles. In fact, in any cycle with more than 3 nodes, it is exactly equal to 0. Clustering grows with ρ, and reaches rather high levels. We see that there is a drastic difference with the clustering of the randomized versions of each network, which remains close to 0 even for large ρ. The main contribution to clustering in kinship networks comes from small groups of fully interconnected nodes. These are nothing but family groups of mutual blood brothers and brothers-in-law, who become more and more frequent as ρ grows. As they are connected all to all, their contribution to clustering is large. Next plot shows the assortativity, which is the correlation in the degree distribution of neighbor nodes. Assortativity is large and positive if nodes with many neighbors are preferentially connected between them, and is large and negative if nodes with many neighbors tend to be connected to nodes with few neighbors. Numerical results show that assortativity is significantly larger for kinship networks than for their random counterparts, much as clustering. The fact that assortativity is large and positive can again be understood by the presence of those family groups where nodes are connected all to all. In these groups, all sites have essentially the same number of connections, and therefore give a large contribution to the correlation in the number of neighbors. Finally, these are results for the average distance in the kinship networks. Recall that the distance between 2 nodes in a network is the number of node-to-node steps in the shortest path joining the 2 nodes. These are data for a network of 1,000 men. The error bars indicate the standard deviation of the distance over node pairs in each network. We see that the distance decreases as ρ grows. In all cases, distances in kinship networks are about twice those obtained for random networks with the same degree distribution. The network diameter, which is given by the maximum distance all over each network, has the same behavior. As for the dependence on the population size, average distances are systematically larger in kinship networks, but we see that they are proportional to the logarithm of n. Note that the horizontal axis is logarithmic. This is exactly the same behavior as for the randomized networks. And the same happens with the diameter. In summary, the structure of our model kinship networks combines several typical random and non-random features. First, in our model population, kinship networks formed by brothers in blood and in-law are less cohesive than expected by chance. They develop a giant component when the randomness in the children distribution is large, but this giant component is smaller than for Erdős-Renyi random networks of the same size and degree distribution. For maximal randomness in the assignment of children, the degree distribution is Poissonian, exactly the same as for Erdős-Renyi networks. The clustering of kinship networks is much higher than for their random counterparts. Their assortativity is also considerably larger, and the same happens with average distances between nodes and diameter. High clustering and assortativity can be understood by noting that kinship networks are formed by small clusters of highly interconnected nodes, which correspond to family groups of mutual blood brothers and brothers-in-law. These clusters are in turn connected between them by relatively long arrays of nodes, which explains long average distances over each network. As we have stated at the beginning, our model kinship network is the simplest we can imagine within a single generation and including both blood and in-law relations, as defined by the European kinship system. Of course, several possible extensions come immediately to mind. Higher-order kinship relations, such as cousins or more distant in-law relatives, would amount to add longer-range connections in the same networks. One or more marriages after divorce or partner's death would incorporate new kinship categories, such as half-siblings. Note that half-brothers and sisters have played an important role in many historical social processes. Admitting homosexual marriages would add the spouse relation as an extra kind of in-law connection in our single-gender network. Polygamy, which has been and still is very common in certain social groups, would have consequences similar to multiple marriages. Finally, the same idea used here for the relatively simple kinship system of the European tradition may be extended to other kinship systems, where one can find amazing degrees of complexity. An extension that can be immediately incorporated to the model is the effective variation in the number of marriages from one generation to the following, in particular, its decline. Having started by the middle of last century, the decline in the number of formal marriages is a widespread and sustained social phenomenon in many modern societies. Over the last 50 years, Europe has witnessed an average decay of almost 30% per generation, with a peak of 37% in Italy. In the same period, the decay in the number of formal marriages in the United States has reached about 27% per generation. And in the city of Buenos Aires, a highly dense urban environment with a relatively aged population of some 3 million people, the same number has shrunk by about 50% since the 1980s. Although the replacement of formal marriages by other forms of partnership does not completely destroy kinship, it is a fact that in-law relations mediated by informal couples are socially weaker. This gradually leads to social isolation, whose psychological effects have been associated with marriage decline ever since the decimation of the European male population in the Great War. In our model, marriage decline can be introduced at the moment of assigning children to defined sibling relations, by considering a larger number of couples in the previous generation. It can be characterized by a single parameter alpha, lower than 1, given by the ratio between the number of marriages in the two consecutive generations. The immediate effect of this extension is to decrease the mean number of blood links in the population. And this change directly affects the connectivity in the kinship network. These plots summarize the consequences of marriage decline on the giant component of our kinship networks. The graphs to the right show the distribution of component sizes, both for kinship and for random networks. For alpha equal to 1, that is in the absence of marriage decline, we have the results that we have seen before. As alpha decreases and marriage decline becomes stronger, the peak corresponding to the giant component in the kinship network rapidly shifts to smaller sizes. The random counterpart also decreases in size, but the effect is much more moderate. For alpha equal to 0.6, which corresponds to a decay in the number of marriages of 40% between generations, the peak of the giant component is already indistinguishable from the background of smaller connected components. We can say that, below those values of alpha, the giant component is annihilated by marriage decline, and the kinship network becomes completely disaggregated in small subnetworks. In the plot to the left, we have the relative size of the giant component as a function of alpha, both in kinship networks and in their random counterpart. The shrinking of the giant component as marriage decline becomes stronger suggests that a critical phenomenon is taking place at alpha around 0.6. This critical phenomenon should not come as a surprise, as the giant component of Erdős-Renyi random networks also shows this kind of behavior when the network connectivity decreases. In kinship networks, due to their relatively low cohesion, the big difference is that the annihilation happens for larger alpha, when marriage decline has reached some 40% between generations. Alarmingly, not so far from the values in real modern populations. Following common practice in the study of complex networks, the next step will be to consider dynamical processes of social inspiration occurring on our model kinship networks. Thank you for your attention.